Today, we'll be discussing sieve analysis, which is a method used to determine the particle size distribution of soil samples. To put it simply, imagine taking a handful of soil and shake it through a series of sieves with different size holes. The smaller particles will pass through the smaller holes, while the larger particles will be caught by the larger holes. The result is a distribution of particles of different sizes that we can then analyze to understand the soil's properties. Next, we'll be talking about the Atterberg limit test, which is a test used to determine the plastic and liquid limits of a soil sample. Essentially, we're trying to understand how soil will behave under external forces, such as when subjected to loads during construction.
All right, so the procedure for sieve analysis, what you need is a bowl with a sample of the soil that you're analyzing. You need different sieves, which have different sizes based on the square holes in each sieve. As you can see, number 4 sieve here is the largest. And then it progressively gets smaller and smaller until you get to the 200 level sieve, which separates the coarse grained soils from the fine grained soils. To perform the sieve analysis, you put all of the sieves into a stack, starting with the widest holes at the top, so the number 4 sieve at the top, progressively in order until you reach the number 200 sieve with the pan on the bottom. Next, you pour the soil sample into the top. You close the lid tightly, and then you either put this into a sieve shaker, mechanical sieve shaker, or you can also get a nice strong Air Force soldier to shake it.
Shake it and bake it.
If you do shake it manually, make sure you go in circles, not up and down, or you'll get some upheaval of the soil particles, which you don't want. You want everything to go in a circle so that all the sand particles or soil particles can fall down. That way, easily separating all the different sizes into each separate layer. After 10 minutes of shaking, set it aside and give it 2 minutes to settle to allow any fine particles to settle to their respective layer. After that settling, take each pan out and weigh it with the soil sample that's retained. That way you can get the difference between the mass of the sieve without soil and the mass of the sieve with soil, thus calculating the mass of the soil retained on each sieve. From those calculations, you can then determine the percentage grain size of each sieve. So if there was, for example, 100 grams left on the number 4 sieve out of 500 grams, that would be a 20% retained on the number 4 sieve. From these calculations, you can plot your sieve analysis graph, and from that graph you can determine the diameter of 10%, 30%, and 60%, at which that percentage of soil is retained. And from those diameters you can calculate the coefficient of curvature and the coefficient of universality, and from those coefficients you can determine whether the soil is coarse or fine grained. And those calculations are also shown in the presentation.
Hi, I'm here to talk about the Atterberg test. This is the test you do to classify the fine-grained soil particles after your sieve analysis, or if you only have fine-grained soil. Over here we have Boston blue clay. As you can see, it's been pounded down to like a powder, and you want to make sure it's dry, and then when you're ready you add water, mix it together so it becomes a thick paste, and you use the spatula to mix it. Then whenever you're ready and you think you have the right, because as I said, you want it to be a paste but not too runny or too thick, and then you'll smear it on smoothly onto the Casa Grande device cup or the liquid limit device, and when you have it spread, you want it to be about 10 millimeters thick. You're going to do a scoop right through the middle, make a cavity, You can use this or this to do it, and then you're going to have a chasm in between where you spread out the clay. Then you're going to run the test by just simply going 1, 2, 3, 4. You count the number of blows it takes for the separated chasm to come together. If it takes more than 30, you have more than 40 blows for that to happen. You have to rerun the test and collect more data, but always count how many blows it takes. And then afterwards, you're going to collect the data, put it on a semi-log scale, and you can figure out the number of blows it takes for 25 of these blows to push the clay together, or the fine particles together. That is your liquid limit. As a side note, we need to find the water content of the soil, of the fine-grained particles, whenever we, for each test. So the way we do that is we take, after we run the test and we record the number of blows, we take a small sample, put it in here, and mass the initial weight, right, of the sample with the water. We put it in an oven over here to dry for 24 hours or 8 hours or however long it takes for it to dry. And then we mass the sample afterwards, and we can figure out the water content for that particular test. And that's what we graph with the number of blows on a semi-log scale. And we can figure out the liquid limit.
So the next test is the most frustrating Atterberg test, and that's because you have to take a sample and roll it out to a thickness of 3/8 inch diameter. And once you do that, and it splits down the middle or it cracks, that's defined as the plastic limit of the soil. Once it cracks or splits in half, after rolling it, you put it in here, you put it inside one of these, and then you come over to the oven, you put it inside the oven, put it in, close it, and then leave it for about 24 hours for it to dry. Once it dries and you take it out, you take the mass of before, because you wait before you put it in the oven, and then you take the weight or the mass of it after it comes out the oven. You find the weight of the actual soil by measuring this while it's empty, of course. That's the tare, basically. And then afterwards, you can define what the moisture content of the soil is at the plastic limit. And this is kind of an arbitrary method created by Atterberg, because he's like, how can we define the Atterberg test? Well, we'll make it a standard. If you can roll it to this diameter and have it split in half, then that's what the plastic limit is. It's a pretty straightforward test and a very simple way to classify the soil, and that's what it comes down to for these Atterberg and sieve analysis tests, is actually classifying the soil. It's a basic, fundamental principle of soil mechanics and geotechnical engineering. Because when you go to a soil site as a project engineer or geotechnical engineer, and you want to know what kind of soil they have on site, the construction workers or whoever the geotechnical engineer is, they'll say, hey, we have a some sand with gravel inside or whatnot, like silty sand, something along those lines, and it's actually classified by the USCS, Unified Classification Soils, something. It doesn't matter. The point is that you can easily classify the soils using this approved graphs. Is what it comes down to. Is they just they give you this graph, the ASTM, American Society of Testing Materials, and you can plot your liquid limit against your plasticity index. And the plasticity index is determined by taking the liquid limit, which was determined from the previous Atterberg test with a Krasser-Grande device, and this test, which found the moisture content of the plastic limit, and you take the liquid limit and then subtract the plastic limit, and you get the plasticity index. And by graphing the liquid limit against the plasticity index, you can determine the classification of soil, of the fine-grained particles. And that's about it for now. I think everyone had a lot of fun doing these tests, because it takes a lot of patience, so it definitely develops a person. And that's about it.